So Cellular Automata. In this case, we're going to first look at Conrad's Game of Life, and then we're going to look at Cyclic Cellular Automata. Cellular Automata is a iterative simulation where each pixel will change given a rule set. Now, we've previously, of course, taken pixels, had them look at their neighbors, and then done something with the pixels. The difference is, roughly speaking, as Cellular Automaton tends to be interpreted in several different ways, is that we have some conditions for what will happen. So the classic one is Conrad's Game of Life. So we press play and press start here. We can see it's like there is its own life in here. There's some rules that makes these, they're called gliders, come out of this thing up here called the gun. And they are all just generated based on some very basic rule sets. So if we look inside the material, we once again are using our convolute kernel function, and we are just feeding in a weight of 1 for every single neighbor pixel, and then there's only a 0 right here for the center pixel in the center row, which is currently processed pixel. This will give us a count of how many pixels are alive, represented in white, and we can then apply some rules to that. And here we have two if statements, and basically what they sum up is that if a cell has 2 alive neighbors, it will survive if it's already alive, and if it has 3 alive neighbors, it will come to life or stay alive, and in all other cases it will die. That's the rule set, and that rule set is all it takes to then get the functionality that we saw in here. Now with cyclic cellular automata, it's a bit different. The idea here, the cyclic part, is that we are not just having a dead or alive state, but we are having multiple states. So the rules for a cellular automaton come in a number of varieties, and they are defined by a chosen range, which is the kernel size, is a number of pixels. That would account for the same thing as when we were looking at the texture-based kernels. What is the size of the kernel texture? There is the threshold, which is how many of these neighbors have to be one larger than our currently processed pixel. And then we have a number of states. And the number of states is what defines the cyclic part. If we had a max state and didn't do more than that, then a pixel would reach this state and just stay at this state, because it would need pixels around it to be a larger value before it could increment itself again. Because you can imagine that every pixel will always be looking for pixels around it that is just one larger than itself. So if this one has a value of 2, it will look in, for example, these, or potentially even these, or maybe even these, and it will look for some that are a value of 3. However, if 3 is the maximum, and it finds them and then increments to 3, then we're done. Then there's not really anything else to do, right? Because next time it looks around, it'll just find 3 again, but it's already 3, so it stays 3. So what we do is that when we reach the max state, if we say that the max state is 3, it's not actually looking for 3 around here, it's looking for 0. So we go 0, 1, 2, back again. And this is what makes it cyclic. This is what makes it cycle forth again and again through the same, so that this is how we get this propagation and the effects that we see with it. And there are sort of a few different states that it can take. It will either stall completely, keep cycling, or find some sort of equilibrium. And let's have a look at 2 of these cases, one for cycling and one for equilibrium. So the first one we're going to look at is going to have a range of 3. That means that we will go 3 pixels out from the currently processed pixel, giving us a 7x7 kernel. It will have a threshold of 10, which means that it has to find 10 pixels within this neighborhood, all with a value of 1 larger, or if it has the maximum value of 0. There are only 2 states, which will really mean that the values can really only be 1, 2, 1, 2. That's cycling back and forth between these two. And we're not having the square kernel on, we're using a von Neumann, which I'll show in a bit what that really means. So when we press play, you can see that it reaches this state where it doesn't completely converge until a bit in. You can see it keeps jittering, and this is sort of the stable state, the equilibrium, where it finds a point, it's just cycling back and forth between the same two frames. A stalling choice is going to be most of the configurations that you choose. You can try playing around with that. But a cyclic one that we can try is one that just goes a range of 1. So that's a 3x3. A threshold of 1, which means just finding one that matches the criteria. And then we go all the way up to 16 states. And in this case, we're going to use a square kernel. So we're going to use a more neighborhood. And in this case, you'll see this beautiful pattern, and from it, there will emerge these spirals. And you can find more rules online. For example, here is an entire list of them. Do keep in mind that some of them depend on the initial state. So even though it is random, it's very dependent on whether or not the randomness is as uniform as it can possibly be, or if there's a little bit of spatial seeding offset. So the noise that I'm using is not necessarily the one that will give the most uniform distribution of the values. However, it gives the best results for things like the 1/116 spirals that I showed. All right, so let's look at the material for cyclic cellular automata, because it is this tad bit more involved. So we're just copying all our values over into Visual Studio Code. We are doing the usual with getting the dimensions so that we can go 1 pixel over. We are using indices here and the load function. We then load our center value. We then find a search value. So the search value is the current center value plus 1 modulus the number of states, which means if there are 3 states and this is 2, we will look for, well, 2 plus 1, that's 3, but then we roll back to 0 because of this. We then once again sum up how many matching neighbors we find. And then we have our 2 loops, but you can see a little bit is going on inside here for these loops. Let me just draw it out for you. So here we see a kernel with a range of 2. This means from -2 to +2 in both directions. If it's a more neighborhood, then we will be using all 24 values. So that's 5 by 5 minus the central one. And if it's a von Neumann, we're going to do the diamond shape. So basically what we would be doing is we would start with I equal -2. So we would start with this row over here. And then we would say, great, in a more neighborhood, we would then go, the -2 and then the -2, and then we would go down here. But before we do this range, we say range is 2 minus 2. So that is range 0. So we only get this one because we only iterate once with an offset of 0. And then in the second one, it is a range of 2 minus 1. So we get a -1, 0, and 1. And so you can see the ones we start populating with the von Neumann are the diamond-shaped ones. So we took the absolute value of the I index, so it will go 2, 1, 0, 1, 2, subtracted from 2. So 2 minus 2, 2 minus 1, 2 minus 0, 2 minus 1, 2 minus 2. And when we get to 0, we still do one iteration. So hopefully that clarifies the meaning of these names. So now we get into the J loop. And the first thing we do is make sure that we have not reached the currently processed pixel, meaning that we're not processing the center pixel where the index is 0 for both I and j, in which case we just skip this loop. The next thing we do is that we get our sample index, and which we do by taking the pixel index that we found in the beginning, and then we add our I and j offset to that. We then make sure that we do not go outside the texture area. So if we do this, the load function will just return 0. So it will be as a minimum 0 as an index value, and as a maximum it will be the size -1. We then load the pixel, And then we just ask down here where we had already found the search value, if we subtract the search value from the found value and we take the absolute of that, we get a value that's going to be smaller the more alike they are. And then we just have a relatively high tolerance here because we're comparing whole numbers. So 0.1 is definitely decent. The reason why we do this and not just equal equal is this guarantees that we not get any rounding errors obstructing our comparisons. If there is a match, we increment matching neighbors. So when we are done with looping our entire neighborhood, we check if we found so many matching neighbors that it either reaches or exceeds the threshold that we piped in. And if it did, then we just return the search value because that is our current value incremented with 1 and potentially looped back to 0. Otherwise, we basically just return our current value, which is going to make no change. So yeah, that is all there is to Cellular Automata.